We present a parameterization technique that can be applied to surface meshes in real time without time-consuming pre-processing steps. We propose a local optimization approach that is suitable for parallel execution on the GPU, achieving on-the-fly texturing of 3D surface meshes. In this way, live parameter updates and determination of varying texture coordinates can be performed in real time. This works even on animated surfaces of morphology-changing meshes, as well as for the visualization of dynamic vector fields. Here, we see an artificially generated example where two moving spheres representing vortex cores generate a dynamic vector field on the surface. Due to the globally continuous pattern that is generated every time step, we are able to update changes to the flow, as well as parameters, on the fly. Close to the vortex cores, we visualize the vector field with an animated arrow texture, while further away, we animate the field with a less salient texture to emphasize the flow around the vortices. In addition, the surface parametrization can be employed to provide a focused and context-style visualization with the whole liver as context and the region around the needle tip as a focus region. By selectively discarding fragments, a clear view on underlying structures close to the needle, such as the tumor and vessels, can be given, while still providing a spatial impression of the whole organ. We call this binary transparency. The advantage over actual transparency is that the colors of the underlying structures are maintained. Thus, we can employ a color map to encode the distance of vessel and tumor without interference of transparency and color. In this example, we see a surgical guidance scenario on a liver dataset where the vessel striping is updated on the fly to reflect the current distance to the needle tip. Here, the total stripe width represents 1/10 of the local distance to the needle tip. If the distance is 1 centimeter, the total stripe width, black and white, will be 1 millimeter. High-frequency striping indicates the needle tip is close to the vessel. The parameterization can also be used for general illustrative rendering styles. For example, we are able to draw locally varying hatch strokes or to render only a dashed silhouette to obscure less important parts of a mesh. Our technique is able to generate strokes of adjustable width and spacing and allows dynamic stroke directions without pre-computation. Here, we employ a frame-by-frame update of the parametrization to drive a hatching shader for animated meshes. By mapping the light intensity to the parametrization frequency, we are able to implement stippling for dynamic objects. This is an example demonstrating visualization of a stress tensor on aneurysm surface data. The first eigenvector projected onto the surface is represented by the pattern, and the first two eigenvalues are shown in green and orange. Purple and magenta indicate areas where the respective eigenvalues exceed a user-defined threshold. While zooming in, the frequency of the pattern increases to allow for more detail. Thank you for watching.